Mhm. Just wait a second. Yeah. Hello, everyone. In this week's QTFMS seminar, we will be having Alison Warman from the University of Oxford. And Alison is going to talk about phases with generalized symmetries. So, Alison, you can take it away anytime you want.
Thank you very much for the invitation to this really interesting seminar series. Okay. And today we're going to talk about phases of generalized symmetries from the SymTFT. Indeed, Landau already realized that symmetries are key for classifying phases of matter. However, in the last 10 years, we have realized that symmetries go far beyond groups and include many different kinds of generalized symmetries, such as higher form, higher group, or non-invertible symmetries. To study all these generalized symmetries, we can use the Symmetry Topological Field Theory. And this enables a systematic classification of quantum phases of matter with any generalized symmetry, and doesn't only reproduce known results, but gives us the systematic classification and enables us to uncover new and unexpected phenomena and examples, which I will illustrate in 1+1D and 2+1D. First, let's just start by reviewing the notion of generalized symmetries as topological operators. So as we all know, an ordinary symmetry is an operator U of t, a unitary that commutes with the Hamiltonian. Because of this, it's preserved in time. So U of t is equal to U of t prime. Furthermore, U acts on a local operator by conjugation and returns the operator multiplied by the representation of that operator under the symmetry. Its charge to encompass a broader class of symmetries. Well, the fact that the operator commutes with the Hamiltonian and is thus conserved can be interpreted in a Euclidean spacetime QFT perspective as the operator being topological. This means that if we deform it in time, it doesn't change, and so the generalization is as if we deform it in spacetime, the operator is the same, unless it crosses charged operators. In that case, we will pick out the charge of the operator. So in this paper by Gaiotto, Kapustin, Seiberg, and Willett, generalized global symmetries were identified with these topological defects in a QFT. Indeed, we can think of this U of t acting on all points as being supported on a space manifold that can then link with the operator returning its charge. However, this idea of generalized global symmetries as topological defects enables a huge class of generalizations compared to the standard invertible symmetries acting on a local operator. For example, we can have topological defects that link non-trivially with extended operators. So, for example, if we have UP, a space-time dimension P, this can link with a topological defect of dimension D minus P minus 1. And in that case, we can obtain it will give us the charge of OP under this generalized symmetry, D generated by D, which is a higher form symmetry, since the operators charged under it are not local operators, but have a higher space-time dimension. And these type of symmetries are already present in Maxwell theory, because since F is equal to dA, dF is equal to 0. And if we don't have any matter, d star F is also equal to 0. So if we integrate F and star F, and then we deform the manifold, and then we use Stokes' theorem here, the U operator doesn't change. So in this sense, they are topological thanks to these equations of motion. But they are integrated on a two-dimensional surface, so not on the whole of space, so they are not ordinary symmetries. Indeed, the operators charged under these are lines. Specifically, they are the so-called Wilson lines, which is the integral of A of the gauge field, which is charged under this electric one-form symmetry, and the Toff line, which we can think of as the integral of the dual magnetic gauge field, which is charged under this magnetic symmetry. So we already see one-form symmetries in this very simple Maxwell example. In Yang-Mills theories, we can also have one-form symmetries, and they can be used to characterize confinement, because if we have deconfined quarks, they will be attached to world lines to be gauge invariant, and these lines are charged under one-form symmetry present in Maxwell theory. So if this one-form symmetry is spontaneously broken, we have lines operators charged under it, and it means that the quarks can live deconfined in a deconfined manner attached to these lines. Whereas if the quarks are bound into baryons and mesons, that means that we don't have these lines, and so the one-form symmetry is not spontaneously broken, it's preserved. Another example of one-form symmetries was understood by Kitaev, even though not in that terminology, on a torus. So if we have topological lines on a torus, here shown in blue and red, which obey Z2 fusion rules, we can have a Z2 times Z2 one-form symmetry. And furthermore, if they have a mixed anomaly, which means that basically there's a -1 phase if we unlink them, these can be shown to encode the quantum information operations for qubits. This is because these two topological lines form, as I said, a Z2 times Z2 symmetries. So we can think of them as basically Pauli X and Pauli Z. And the -1 phase from unlinking is basically the topological characterization of this anti-commutativity property of the Pauli matrices. So this is a way to describe a topological quantum error correcting code as understood by Kitaev. And why is it very interesting that since these lines are topological, it means that the code is very robust against local errors and noise, which can happen in realistic quantum computers. So this is a proposal for fault-tolerant quantum computing. So okay, there's a question. Is there a question?
Yes. Good
Yeah.
morning.
Hello?
I have a question. From the beginning, almost in the beginning, when you write UDT and UT prime, in some sense, these are the time evolution operators, right? So
Yeah.
you are saying that the evolution it's not depending of the time. So this is a little weird because usually it depends only of the difference of the times, right? The time of evolution operators it only affects in difference, not in every part of times. This
Yeah,
is weird.
sorry, so here U of T is not the time evolution operator. U of T is a symmetry. So the Hamiltonian generates the time evolution. So I know, sorry, unfortunately, U of T is the notation that's used for many unitaries. But
Okay.
here, U of T is not the integral of the Hamiltonian. It's another unitary operator that commutes with the Hamiltonian. So, okay, the Hamiltonian itself commutes with itself, but that's, that's not usually what we think of as a symmetry. So in this case, we have a Hamiltonian, and then we have an operator, which is a unitary that commutes with the Hamiltonian. So a general operator could depend on time, and as you say, would evolve under the time evolution generated by the Hamiltonian. But since this operator commutes with the Hamiltonian, and the Hamiltonian generates time evolution, but this commutes with it, it means that this particular operator is actually preserved in time. So it gives rise to a conserved charge. There's a very nice relation between symmetries and conserved quantities.
Okay. A little
Yeah.
better.
Yeah,
Thanks.
but thank you for the question. As I said, here U of T is an operator that commutes with the Hamiltonian.
Thanks.
And because of this, it's preserved, and the generalization is that it's topological. Thank
Okay.
you. Are there any other questions? Okay, so now we can go on. In general, the fusion of topological defects doesn't have to obey a group law. And in particular, they can have these so-called non-invertible fusion rules. So if we take two topological defects, we can have a sum of other topological defects, in general with topological field theory coefficients. So these have been described already into the conformal field theories. Now, the mathematics behind them in higher dimensions is that of higher categories. But they have been explored subsequently in physical contexts, also in higher dimensions. So even though the mathematics appears very advanced and abstract, they actually are present in very simple, relevant physical theories as well. Now, we want to describe phases of matter. So what is a phase? Now, a phase in the first instance is basically a ground state of a Hamiltonian. So if I want to describe a pure state phase, this is just the ground state of a Hamiltonian, where the Hamiltonian is required to be local, and in general, we can have symmetry. So if we want to describe a gapped phase, the Hamiltonian should also have an energy gap, okay? And these gapped phases are also called topological phases. However, a phase isn't just a ground state, it's actually an equivalence class of ground states, where the ground state's actually related by U, which is not a symmetry. This is the time evolution operator, as you were saying earlier. So this is now the time evolution operator. And if two states are in the same phase, it means that there is a time evolution between them, which is given by a gapped h of t that can interpolate them. So this means that if we start with one phase here, and then we perform time evolution with h of t, we will obtain another phase. And if we always have the gap, these phases have the same these ground states have the same symmetry properties and are in the same phase. However, if such gapped Hamiltonian doesn't exist that can interpolate between the phases, they are distinct in equivalent phases. And along the time evolution, there will be a point in which the system undergoes a phase transition. So we'll have a gapless degrees of freedom and a change in the physical properties of the system. So a very nice example of this is the transverse field easing model in 1+1D. So we can write a Hamiltonian with the Pauli matrices as Zj plus 1 and then Xj. Okay. So this Hamiltonian has a Z2 symmetry given by the product of X. Indeed, X is obviously commutes of X, and so does ZZ, because a single Z will give a minus sign, but with two of them, it commutes. So this Hamiltonian describes three distinct phases. If we have G greater than 1, we have a single ground state, which we can write exactly in this way for G very large, and this is the +1 eigenstate of X. So if we write as spin up and spin down the eigenstates of Z, then the eigen and X exchanges spin up and spin down. Then the eigenstate of X, the +1 eigenstate, is spin up plus spin down. And this clearly minimizes the Hamiltonian for G very large. If instead we have G equals 0, or more generally G between 0 and 1, we will have two ground states. For example, for G equals 0, the Hamiltonian is just Zj plus 1. So we can obviously have all spin up, because these are the +1 eigenstates of Z. But we can also have all spin down, because if we act with Z on a single spin down, we get -1. But here we have ZZ, so the two minus signs will cancel. And these are both degenerate. These are both ground states, and they are degenerate here too. So we have these two different phases, which clearly have different physical properties. Here we have a single ground state that is preserved, in which the Z2 symmetry is preserved, whereas here we have two different ground states in which the Z2 symmetry is spontaneously broken. It's spontaneously broken because the Hamiltonian is still invariant under the symmetry. So if we have a Hamiltonian that's invariant under the symmetry, but the ground states are not, we say that the symmetry is spontaneously broken in that phase. And if we interpolate between them, so if we set G equals 1 in this Hamiltonian, this is actually a conformal field theory. So we have gapless degrees of freedom, and indeed the system undergoes a phase transition with changes in the physical properties. Furthermore, this Hamiltonian doesn't just have the Z2 symmetry, but at the critical point, if we set G equal to 1, we see that this ZZ term and the X term have the same weight. So there's also another symmetry known as Kramers-Warnier duality, which basically sends X to ZZ and ZZ to X. However, this cannot be implemented by a unitary, by an invertible operator. It can actually only be realized by a non-invertible operator, which obeys these fusion rules. We will see in more detail how this can
Can I
be
ask something?
implemented. Yeah, sure.
When you talk about the phases, what do we actually call different universes here?
Okay, so usually a universe is what one calls basically a ground state which has gapless degrees of freedom as well. So for gapped phases, we can talk about ground states. For a gapless phase, since we have basically an energy gap, we don't have an energy gap, so we have a continuum of excited states. rather than using the terminology ground state, one talks about universe. So in this case, there is a single universe here because there's just one CFT. But we will see examples in the following in which, rather than having just a single CFT, we can take, for example, the Ising CFT, and then basically take a tensor product with a Z2 broken phase. In that case, we will have then two Ising CFTs. You can think of this as, yeah, basically taking Ising. If we have like some more qubits, some more states, we can put Ising on one the states, and then we can take a tensor product, for example, first by spin up and then by spin down. So in that phase, we will have actually two Ising CFTs, so two universes. So basically, universe is the terminology that's used for ground states of a gapless theory.
Yeah, okay, thank you.
Good.
Can I also ask a question?
Yeah.
Is this notion of universe different or the same as in the notion of universe when we have d-1 form symmetries in d-dimensional quantum field theory? Because I'm not sure if it's the same. It doesn't the same.
So yeah, basically what happened, so when we have some spontaneous symmetry break-in of a certain symmetry, the ground states can be grouped into like in equivalent, like into different classes that are related by the symmetry. So we can call each of these a universe because each of them is a particular ground state, but then the symmetry acts on them and relates them to each other.
But this doesn't necessarily mean that we have a topological local operator, right? So there's like
no, actually,
it's distinct from the notion of universe.
The notion of universe, yeah. So the notion of universe that I'm familiar with does imply that we have topological, like if we have multiple universes, it means we have multiple topological local operators that can distinguish the different universes.
Okay. Okay.
Yeah. We will see some examples in the following, yeah.
Okay.
Yeah, it might become clear. Thank you. So here, for example, if we want to see how these fusion rules can be computed, one can use the property that in a CFT, one can have so-called Verlinde lines, which are topological lines, whose action on the primary fields can be computed from the so-called modular S matrix. And therefore, one can write these eigenvalues under the symmetry. And for example, from these eigenvalues, we can determine the fusion rules. So as we see, for example, eta flips the spin here, sigma, but n annihilates it. And so already from this, we can see that it's non-invertible because it has a zero eigenvalue. And then, so if we apply n twice, we will get obviously 0 on sigma. And this is the same as the eigenvalue of 1 plus eta. And similarly on epsilon, if we apply n twice, we will get 2, which is the sum of 1 plus 1, and same for the identity. So this is a way to derive the fusion rules of the non-invertible symmetries from conformal field theory. So before we go into the main part of the talk, I just wanted to emphasize how generalized symmetries really connect many different research fields. So they basically originated in high energy physics, but as we see, they have many implications in condensed matter physics. They're described by advanced mathematics and can also give rise to new ideas and proposals for quantum information. Are there any questions on this introductory part? Or good. So let's start now with the main part of the talk. So our main character is the symmetry topological field theory, or SymTFT. So if we want to describe the symmetry properties of a particular theory, T, it's very useful to separate the generally complicated dynamics of the theory from the topological symmetry properties. So the SymTFT enables us to do this. It is a topological field theory in d+1 dimensions with a topological boundary that fixes the symmetry. So on this boundary, the symmetry generators live, okay? Whereas the physical boundary encodes the dynamics of the theory. So in general, these dynamics can be very complicated and the theory can be non-topological, but this is only on this boundary. Then all the rest of the SymTFT is topological and enables us to basically do all these symmetry calculations in a general manner, independently of the complicated dynamics the theory may have. In particular, charges of operators can be computed from the link-in action in the SymTFT bulk. So, for example, here we have a topological operator A and a B that links with it. And a very simple example of a SymTFT is for Zn symmetry, where we can write it as the BF theory. So B and A are just these gauge fields. We can write this action in d+1 dimensions. And if we perform canonical quantization of the action, we will see that if we commute B and A because of this term, we will get a link-in phase. So we get e to the 2 pi I over n times the link-in of the manifold. So if the two manifolds intersect, we will get this phase. And this basically will tell us that A is charged on the B as a generalized symmetry operator, okay, where this is the charge. These are some references on the SymTFT for discrete symmetries, continuous symmetries, and quantum phases, including the references for this talk. Now, from these topological defects in the SymTFT, how do we get the actual symmetry generators? So these will be topological defects, dk, which can live on the symmetry boundary. So these are not the defects that can end on the symmetry boundary, because see here, A, for example, can end on the symmetry boundary, so it becomes trivial. Whereas D, in this case, remains a topological defect and generates a particular symmetry. Instead, the charged operators will be given by these defects that can end on the physical boundary. So in this sense, they are operators in the physical theory. And they can also end on the symmetry boundary and have some link in here with the bulk topological operators. So if they also end on the symmetry boundary, they will have dimension P. Otherwise, we can also consider defects that end on the physical boundary, but also extend on the symmetry boundary as well. But all the defects that end on the physical boundary will give rise to charges under the symmetry. Now, when
I have a question about the second bullet point here. Does this mean that if you have like a quantum mechanical system, there cannot be any non-invertible zero-form symmetries, or doesn't imply this?
So for a quantum mechanical system, you mean
yeah, like D equals 1.
plus 1D.
D equals 1 plus 0.
1 plus 0. So the TQFT would be two-dimensional, would be just one-dimensional. So okay, I think for quantum mechanical systems, you can have non-invertible symmetry, like you can have non-invertible symmetries for quantum mechanical systems.
Okay. Is there an example?
Yeah, so for if you take, for example, there's you can definitely write non-invertible operators acting on a Hamiltonian. So for example, if you just take a Hamiltonian with a Z2 symmetry and then you take 1 plus the Z2 generator divided by 2, this is non-invertible, but a commuted Hamiltonian. However, in this sense, so you can trivially write these kind of non-invertible operators that commute to the Hamiltonian, but in general, they don't give rise to new symmetry properties. However, we will see examples of Hamiltonians in one dimension which have generalized symmetries.
Okay.
Yeah, so we'll see them. Then we can get the various kind of phases by choosing different physical boundaries. If the physical boundary is also topological, it will give rise to a gapped topological phase. Whereas if the physical boundary is non-topological, we can have these gapless phases, for example, with phase transitions. Now, what I want to emphasize is that the SymTFT allows a very systematic and general exploration of all these kind of phases and enables us to generate these new interesting examples with unexpected properties. Now, before we come to the examples, let's just discuss a bit more in general what happens with a gapped symmetric phase. So we'll have the symmetry boundary, which is topological, and we'll have some defects that can end on the symmetry boundary. So these are not the symmetry operators, because the symmetry operators are the ones that live on the symmetry boundary. These ones become trivial on the symmetry boundary. And then we also they can also end on the physical boundary, so they will give rise to charged local operators, because as we saw in the previous slide, if these link with the symmetry operators, they will be charged under the symmetry. So we'll have indeed multiple topological local operators. If there were multiple of these, they will have more than one ground state. So if there's only a single one, the phase will be symmetric and a so-called symmetry protected topological phase. If instead we have multiple topological local operators, we will have multiple ground states for gapped phases or universes in the gapless case, distinguished indeed by these topological local operators basically in each phase. We take linear combinations of them, and the symmetry will permute these different ground states. So whenever there's spontaneous symmetry breaking, we will have multiple ground states. Now, importantly, in higher dimensions, we can have not just zero form symmetries, but also higher form symmetries, and spontaneous symmetry breaking for the higher form symmetries as well. And if a phase which exhibits SSB for a high form symmetry is called topological order. So in that case, we have multiple ground states on topologically non-trivial manifolds like the torus that we saw before. And in that case, the distinct ground states are related by the higher form symmetry operators. We can systematically classify all these phases by basically generating all the possible maximal and non-maximal condensation patterns of the topological defects. And by using the SymTFT to perform the calculation for their symmetry properties, we can classify all these kinds of phases as SPT phases, which can be gapped or gapless if there's just a single ground state, or SSB phases in which we have multiple ground states related by the symmetry. And interestingly, for the gapless phases, we can have so-called intrinsically gapless phases, in which we have some symmetry properties in the gapless phase that are not exhibited by the gapped phases that they can be deformed to. So, for example, an intrinsically gapless SPT can only be deformed to spontaneous symmetry breaking phases. So even though this has a unique ground state, it can only go to phases with multiple ground states. So all these phase diagrams can be computed by basically calculating all these anion condensation patterns and then using a subalgebra property. So this phase can be deformed to this other one if it is a subalgebra. And in general, it's not enough to just give the list of topological defects because the algebra structure could also play a role. However, in simple examples, we can just write the topological defects. For example, for Z2, if we consider the SymTFT for a group, the anions in so the topological defects in the 2+1 DTQFT will be labeled by a conjugacy class, so of these group elements, and a representation of the centralizer group, so of the group elements that commute with it. So for Z2, if we denote the Z2 group elements by plus and minus, and the representations by 1 and 1 minus, we have 4 anions, the identity, then E, which carries the non-trivial representation, M, which carries the non-trivial group element, and EM, which is their product. Now, when we classify these boundary conditions and the non-maximal algebras, we can only condense bosons. So often one uses this terminology of anion condensation for the SymTFT, and this refers to basically this is boson condensation. So we make these bosons trivial, they become the identity. So they all go into the ground state. For Z2 symmetry, we need to fix a symmetry boundary that we take to be 1 and E. This means that E can end on that boundary, but M remains non-trivial, and M is this non-trivial Z2 group element, so it generates the Z2 symmetry. We will fix this as the symmetry boundary, 1 plus E, and then if we choose this as the physical boundary, we will have 2 ground states, because 1 and E can end on both the symmetry and the physical boundary. And since E is charged under M, because M is the group element and E is the non-trivial representation and there's a minus sign charge, here we will have 2 ground states which are exchanged by the Z2 symmetry. So this is the Z2 spontaneous symmetry breaking phase. If instead we take 1 plus M on the physical boundary, here we don't have any charged operators, so we just have 1 ground state and we just have this trivial symmetric phase. If we interpolate between them, then there's a phase transition, which is described just here by the identity anion. We can now move on to a more complicated example, where we consider the group of symmetries of a square, which we can also write in terms of Z2 times Z2 times Z2 with a semi-direct product, because the group is non-abelian. So it's Z2 times Z2 with a semi-direct product. And the reason we choose to represent it like this is that we can map it to a Hilbert space of 3 qubits. This is 8 group elements, so we can realize it on 3 qubits. And the representations of this group are as follows. There are 4 one-dimensional representations, but since the group is non-abelian, there's also a 2-dimensional representation that obeys this fusion rule. As we see, 2 times 2 is consistent with 1 plus 1 plus 1 plus 1, the dimensions. And this means that this is a non-invertible symmetry. So we can label the anyons in the SymTFT as this, and we can map out all the phases. So this is the full phase diagram. And in particular, so for this non-invertible rep-D8 symmetry, we can also have an IGSPT phase. So this is a phase that has a single ground state, but it can only be deformed, so a single universe in this context, since it's gapless, which can only be deformed to a gapped SSB phase, but not to an SPT, whereas a standard GSPT can also be deformed to an SPT. And then we can also have intrinsically gapless SSB phases, which increase the number of vacua when we gap the theory. Furthermore, we can
I ask
also...
one question about your terminology?
Yes.
Because I'm still confused about when you say a universe, do you mean a universe in the SymTFT or in the physical theory?
No, in the physical theory. That's after we
Okay.
compactify the SymTFT.
Okay.
Yeah, thank you for the question. Yes. So
Okay.
we have the SymTFT here. Then after we shrink the slab, in the theory, we will have these local operators. And we can take a linear combination of local operators. So we'll have basically the same number of states as the local operators. And each of these will be a universe.
Okay.
Furthermore, we can realize this we can write very concrete spin chain Hamiltonians from this symmetry. Basically, and implement them, and we proposed an implementation on Rydberg atom arrays setup, where we have on each site, 3 qubits, because here we have Z2 cubed, Hilbert space. And this silver atom can be used to mediate interactions between the top and bottom qubits here, whereas the golden one can be used to mediate inter-site interactions. And then we can write Hamiltonians, which will have a local on-site interactions here on I, and we can just implement them here in parallel, and then inter-site interactions between I and I plus 1. So basically, by repeating these 2 types of steps, we can implement the Hamiltonian evolution for these phases and verify the SymTFT predictions. So these are the type of gapped phases that we can get with rep-D8. And as we see, there are SPT phases that preserve the full symmetry. There are certain phases that in which an invertible symmetry, shown here in green or red, exchanges them, and a non-invertible symmetry, shown here in blue, sends one vacua to the sum of the other 2. Then a phase in which the ground states are invariant under the invertible ones, but are exchanged by the non-invertible symmetry. Then another phase where we again see the non-invertible symmetry action. And then finally, the rep-D8 SSB phase, which has 5 ground states. And the Hamiltonians can be written very concretely with Pauli matrices. This is the general form of them, with a projector onto a particular subgroup, and then left and right multiplication operators for elements in the group. These Hamiltonians are invariant under rep-D8 and can be used to write explicit realizations for these phases. So, for example, the rep-D8 SSB phase I think is really interesting because this can really only be explained by non-invertible symmetries. So this is a Hamiltonian, the Hamiltonian for it, which is written really just with the Pauli X and Z operators. However, so this is just literally a Hamiltonian of Pauli matrices, but to explain its ground state degeneracy, we need non-invertible symmetries. Because if we only use the invertible symmetries, shown here in red and green, we can only map out the first 4 ground states. The 5th ground state is only sensitive to the non-invertible symmetry. Indeed, we can write them concretely as follows. So the first ground state is just a tensor product of the sum of all the superposition of all the states on each site, of all the qubit states on the site. So there are 8 states here. We just take the superposition of them. And this is just trivially, this is symmetric under the rep-D8. And then when we act with the rep-D8 symmetries on them, we can get the other ground states. If we act with these invertible symmetries, 1A, 1C, and 1CA, we will get some other ground states that are also tensor products. But then if we act with the non-invertible symmetry, we'll get this 5th ground state. As we see here, this is only charged under the non-invertible symmetry. And if we apply it again, even though we started with ground state 1, if we apply it again, we will get the sum of all four. This follows from the non-invertible symmetry fusion rules, and we see that there's a non-invertible action. So if we start with ground state 1, then we go to ground state 5, but then when we act with SE on ground state 5, we get the sum of the other four. So we can't go back to the same phase. So here we really see the non-invertibility. And furthermore, interestingly, while the first four ground states are just tensor products, the fifth ground state is non-trivial entanglement. So this is really Hamiltonian with a ground state degeneracy that can only be explained by non-invertible symmetries, and also different entanglement properties in the ground states, again, as a consequence of the non-invertible symmetry.
Can I ask a question
Yeah.
at this point? In this setup, I can say that in the condensed matter jargon, people just uses topological periodic table for the topological phases for the insulators and something superconductors. So can we just construct some sort of this ideas to construct some kind of, I don't know, again, a periodic table for this gauge theories? Because as far as I understand, we can just construct, I don't know, carton tables and just sort them according to their dimensionality and topological invariance, and just get a topological periodic table for the matter actually, or just gauge theories.
Yeah, so here we can definitely systematically classify these topological phases. So this is a 1 plus 1D phase. Like all these are the 1 plus 1D phases with rep D8 symmetry. So we're inputting the symmetry. We then have the SymTFT. We can write all the anyons and compute these condensable algebras, and each of them will correspond to a particular phase. We are now also discuss some higher dimension examples, which might be more related to the condensed matter examples you were asking about.
Yeah, actually, yes.
Yeah. So here's how we in the phase diagram, the ones at the lowest level are the gapped phases, so the topological insulators, because there's an energy gap.
Oh, yeah, thank you.
But I just want to say that the SymTFT, to my knowledge, hasn't been used to describe, for example, Fermi surfaces where there's lots of gapless degrees of freedom. Here we can describe the gapped phases, so the insulators, and then the phase transitions between them. But to my knowledge, the SymTFT hasn't been used for the, Fermi surfaces and these, very, very gapless phases.
Okay, thank you. Actually, at this point, it could be a bit digression, but do we use any renormalization group techniques or something to diagnose any phase transition between two phases? Because as far as I understand, we talked about the several G's of the Ising model, and and in the paper of the Gomez, I guess it can. He says that we can just add more constraint with the higher form symmetries or something and obtain a RG flow. So are there any ideas to apply to phase transitions?
So yeah, exactly. Because when we map out all these phases, the fact that this is a subalgebra of these other phases means that along an RG flow that preserves the symmetry, we can only go to these gapped phases that are connected by them. Yeah, exactly. So the phase diagram really describes the possible RG flow deformations between the phases. And that's because it's computed using the Symmetry Topological Field Theory, which is topological and sensitive to the symmetry properties. And since the operators in the SymTFT are topological, they commute with the RG flow. So these are like RG flow invariants. And the subalgebra property tells us that along an RG flow with symmetry preserving deformations, this phase can only be deformed to these other two, for example. Yeah, thanks for the question.
Okay, thank you. Thank you.
So we can now also go to higher dimensions, where we can, for example, in 2 plus 1D, if we have just a zero form symmetry G, mathematically, this category is denoted as 2 vac G. This simply means G symmetry in 2 dimensions. But then if we start with this symmetry boundary, we can obtain many other different types of symmetries by stacking with a 3D TQFT, so 2 plus 1D TQFT, which is denoted as M because mathematically it's called a modular tensor category. And then we can gauge a diagonal subgroup. So this will generate various kinds of symmetry. For example, if M is non-trivial, we call these non-minimal symmetry boundaries. If we gauge a normal subgroup, we will have some zero form and one form symmetry, which is still invertible. So this is called the 2 group. Otherwise, if we gauge a non-normal subgroup of G, we will get some non-invertible zero form symmetries. And this can be, for example, like a 2 representation of a 2 group. So as we saw in 1 plus 1D, if we gauge a non-abelian group, we can get rep G, which is non-invertible. In 2 dimensions, similarly, we can have non-invertible symmetries by gauging, starting from a group and gauging some subgroups. So this is an example of non-minimal symmetry. So in this case, we start with G, which is, we just take to be Z2, and then we stack the TQFT given by easing times easing, okay? So here we have the topological lines, which are 1, eta, and n. Now there's a Z2 grading here, because in the fusion rule, we have n times n is equal to 1 plus eta. So if we assign sign -1 to n, we see that -1 times -1 is 1. So in a sense, the easing fusion category is Z2 graded, because we can assign a grading, so a sign to these 2 components, and the fusion rules preserve it. Therefore, we can gauge a diagonal Z2, where the Z2, okay, for Z2 it's clear how it's defined, and for the easing, it's defined by this grading. And then after gauging it, we are left with 4 of these invertible topological lines, and then this non-invertible n bar. So this forms a non-invertible 1 form symmetry, and in particular, this eta bar invertible line is attached to the Z2 symmetry line in the bulk of the SymTFT. We can also have higher group symmetries, in which basically there's a zero form symmetry, shown here in red, that can act on 1 form symmetry lines like this and transform them. And instead, if we gauge non-normal subgroups, we can have representations of these 2 groups. So we can have zero form and 1 form symmetries that can be invertible, but also non-invertible zero form symmetries. For example, here, if we again write D8, but now as Z4, the rotations of a square, and Z2, the reflections, Z2x. If we try to gauge the Z2x, R and R cubed, which are exchanged by x, will combine into this conjugacy class 2 surface. And this obeys non-invertible fusion rules. Now, it's interesting to consider the phases where we pick this boundary, the one we've described for this particular symmetry, as both the symmetry and the physical boundary. So in this case, we will have some local operators coming from lines ending on both, because then after we shrink this, this will be just a 0-dimensional local operator, and there are 3 of them. So as we discussed before, if we have 3 topological local operators, we will have 3 vacua in this phase, okay? And these, since these are charged under D2R and D2R squared, they will have this zero form symmetry action on them. But interestingly, we can also have surfaces that can end on both the symmetry and the physical boundary. And then after we compactify the SymTFT interval with this configuration with the surface, we will get lines that are charged under this 1 form symmetry. Because if we start with this group and then we gauge a Z2 zero form symmetry, we will get a dual 1 form symmetry here. And this particular line operator will be charged under this 1 form symmetry. However, we will get this 1 form SSB phase only in 2 vacua. So this is a very interesting phase because we have 3 different ground states, okay, related by the zero form symmetry, but these ground states have different topological order because they have different properties of 1 form spontaneous symmetry breaking. And in particular, this means that they have different long range entanglement because these topologically ordered phase with the 1 form SSB are distinguished by topological line operators in equivalent configurations. So at the level of local correlations, that they're basically the same, but they have non-trivial long-range entanglements given by these anyons. For example, on the torus, the anyons wrap in the whole cycle. We can also
Sorry, I have a question from page 25.
Yeah.
I think it's the page before. Z2 gauge, yeah, exactly. Z2 gauging here means taking the quotient with Z2,
exactly,
right?
exactly.
Yeah, okay, thank you. Mhm.
Yeah. Okay, and there's a way to derive this also if we start with the D8 zero form symmetry and we just write the cosets like this, and then we gauge the normal subgroup. Basically here, we will have these two cosets which are invariant. And so if we basically gauge a zero form symmetry in a vacuum which is invariant, we get the dual one form symmetry, which is, yeah, so we'll have these lines and generating the one form symmetry and the lines that are charged under it coming from the SymTFT. And furthermore, instead, if we consider the other two cosets, these are exchanged by Z2, so these are not invariant. So when we gauge the Z2x, these just combine into an invariant orbit, but there's no one form symmetry in here. So, I mean, here it's actually trivial. There's nothing charged under them. So this is how we get this phase with different one form symmetry properties in the various vacua. Now, are there any questions on this? Otherwise, we can move on to the last part of the talk where we discuss now the extension to mixed state phases. So, as we said at the start, a phase of pure state phase of matter is just the ground state of a local gapped Hamiltonian, possibly with symmetries. However, in general, quantum states won't remain, pure and perfectly coherent. There will be noise, there will be errors that can decohere it. So it's important to also consider mixed states. So mixed quantum states are averages of pure states, described by a density matrix, which is Hermitian, and where we're taking an average with positive probabilities. And we can also describe then the symmetries of the density matrix. As we discussed, in general, these non-invertible symmetries can have these types of fusion rules where they sum to one and then a sum of other operators. And we can describe the action on rho. In particular, we can have an operator that acts on rho, and then if what we get afterwards is again proportional to rho, we will say that the density matrix has strong symmetry, because this means that the density matrix is an average of states that all have the same symmetry eigenvalue under ds. Okay? Otherwise, the state wouldn't be proportional to rho. Therefore, if a density matrix has strong symmetry, it's simply an average of pure states which all have that same symmetry. However, with a density matrix, we don't have to take averages of states that all have the same symmetry, because there can be some kind of some density matrices where we have an average of states, for which if we just act with it on one side, we don't get something proportional to rho because they have different eigenvalues. But if we conjugate rho, then we get rho back. For example, for Z2, if we take an average of states with +1 and -1 eigenvalues, d of rho won't be proportional to rho, but d rho d dagger will, because if we act on on both on the bra and the cat, if they're charged with -1 under Z2, then the two minus signs will cancel and we'll get rho back. So we should distinguish these two types of symmetries for mixed states. Now, how can we classify these in the SymTFT? Well, there's a way to map the density matrix to a pure state and then describe the symmetry action on the pure state. So basically here we're just flipping the bra to a cat, and we should also take the complex conjugate. And then the symmetry action on the density matrix can be translated to a symmetry action on the pure state, on this pure state rho, which is called the choice state, both for the strong symmetry and the weak symmetry. And you also heard about this in Mong Chang's talk. Now, from the SymTFT, we can now classify all the possible phases and symmetry breaking patterns also for the mixed states by using the SymTFT for the pure state, choice state rho. So in this case, since for a pure state we can have symmetry acting both from the left and the right, we should consider the SymTFT for S left times S right. And the symmetry boundary, if we want strong symmetry, so if we want the system to be invariant both under the left symmetry and the right symmetry, would just be the tensor product of the two boundary conditions for left and right separately. However, the properties of rho, in particular hermiticity and positivity, imply some properties on the possible boundary conditions, which are mathematically described by these Lagrangian algebras. So a Lagrangian algebra here is an algebra formed by these anyons, A left, B right. So these are just the topological defects in the SymTFT, and these are non-negative integer coefficients. However, since the density matrix has swap star invariance, This implies that these numbers must be related in this manner, because if we now swap the left and right copy and take the complex conjugate, the numbers should be the same. And the positivity of rho also implies this condition. So not all mixed state, not all Lagrangian algebras are allowed for mixed states. However, if we impose these conditions, we can then classify them all, and we can obtain these phases for mixed states. In particular, we can start with strong symmetry, and then there can be patterns of spontaneous symmetry break-in where only now the weak symmetry is preserved. So these are called strong to weak SSB phases. Furthermore, if we have a strong to weak SSB, then there can also be an SPT phase for the preserved weak symmetry and the strong part of the strong symmetry. We will see an example soon. Furthermore, if we want to describe a mixed state, a mixed phase where we don't just have strong symmetry, but we have weak symmetry, we can start with the SymTFT for a product, left times W right, and then do some condensation so that afterwards we don't just have a product. So we don't just have this, we don't have a purely strong symmetry, but we have some mixed weak and strong symmetry. So this is an example. If we start with rep D8 symmetry, as we saw before for the pure states, we can start with a strong rep D8 symmetry, so on the left and the right copy. But then if we condense this anion, this is charged under E left. So E is the non-invertible two-dimensional representation, and AB carries charge -2 under it. So this is charged under E left, it's charged under E right, but the product of them, in the product, the minus sign cancels. So E left times E right survives, and we have, but since it's the product, E left times E right, this will act on both sides of the density matrix. So we will only have weak non-invertible symmetry. So in particular, we can write this explicit density matrix for this phase. And in this case, it's strongly symmetric under the Z2, Z2 generators. So we can act on rho from the left and from the right separately with the invertible symmetries, and rho is invariant. But it's not invariant, it's not symmetric under the non-invertible symmetry, under the non-invertible strong symmetry, because SE times rho is not proportional to rho. But if we take SE rho, SE dagger, then we get something again proportional to rho. So this is a phase in which we have a weak non-invertible symmetry and a strong Z2, Z2 symmetry. And in particular, this term here also tells us that there's a strong weak SPT between this strong invertible symmetry and the weak non-invertible symmetry. So finally, I also want to mention that using the SymTFT ideas, we can also gain some new insights for quantum information. So we've discussed at length the SymTFT. Now, if we take the same bulk of the SymTFT for a group, this is known as the quantum double D of G. So we can now consider this 2 + 1 D of G. So this is the bulk of a SymTFT for G symmetry. Even though here we're not thinking of it as a SymTFT because we don't have the symmetry and physical boundary. We're just taking its bulk, which, as I said, is called this quantum double. But as I said, it has these anions labeled by conjugacy classes and representations. So the calculations are very similar to what we discussed for the phases. But we can use these now, following basically Kitaev's idea, to encode some logical quantum information states. For example, here we have a configuration of anions where A1 and A2 fuse to A3. So this is a consistent configuration, and it's not clearly non-trivial because we can't, this is a non-contractible configuration of anions. And so this can be used to encode a logical qubit. And then if we start with our logical qubit here, and then we do some, and then time here is evolving upwards. If we then apply this operator, which is constructed by a 2D SPT stacked on this purely spatial surface with some boundary counter terms, because here we have these free boundaries. So in order for this SPT to end, we need to also have some boundary counter terms. We can then implement a topologically protected quantum gate. And in particular, in this paper, we were able to construct the quantum gates for basically any phase. We can do now a rotation on the qubit by any phase, because any type of phase by picking n arbitrarily large. Okay. So in summary, we've discussed how using the SymTFT, we can systematically characterize phases of matter with any generalized symmetry. This is known as a categorical Landau paradigm. And we can obtain all the symmetry properties of this phase, like a ground state degeneracy, charged operators, the phase diagram with the symmetry preserving deformations, the intrinsically gapless phases, then gapped phases with different types of topological order, the interplay between zero form and higher form symmetries. Then we can also write lattice models to test these predictions, as we saw for REP-D8. As I said, in higher dimensions, we can have all these exotic phenomena. Furthermore, we can also extend the SymTFT formalism for mixed quantum states, and it can also inspire us for quantum information applications. So yeah, thank you very much.
Alison, thank you for the great talk. It was really nice to have you. So yeah, let's thank our speaker. And I guess we can have questions now.
Yeah, absolutely.
I have a question about the last slide you had with the triangle quantum double. Yeah, so here this U alpha beta is a SPT, and you said that there's a boundary here. So
Yes,
if you consider this as like an anomaly, then there should be some edge modes, right? What's the
exactly,
interpretation of that?
exactly, absolutely, exactly. So if we have, so here, alpha is an SPT, a 2D SPT, okay? So that's why it lives on this 2D surface. However, the 2D SPT, sorry, is there another question? Okay.
No.
The 2D SPT can't generally end on the boundary, okay? Because as you say, it's basically an anomaly in for 1 plus 1D. Exactly. So that's why we need the boundary counter terms. So we can only basically implement this if there exists a boundary counter term that cancels the anomaly on the boundary. And so this operator U isn't just alpha, but it's U alpha beta. So basically, we take the 2D SPT and then we divide by the boundary counter terms. Because only in that way can it end on the free boundaries. Yeah.
So
exactly.
do you have some modes on this boundary, right? Edge modes or
So
not?
here we're canceling the anomaly on the boundary. Like the thing is, we can compute the counter term. So in the end, we have, so this operator U alpha beta, I didn't write its explicit form, but it's basically alpha of like A1, A2. And then because alpha takes 2 group elements, and then we divide by beta of A1, and then this beta of A2, and then beta of A3 at the numerator. Okay. So we need to basically, what we are applying is not just the SPT, but the SPT that is corrected by the boundary counter terms. So I'm not yeah, actually. So yeah, I mean, the point is that otherwise it can't end on the boundary.
Yeah. Well, my question is, so if we have this like surface, which is an anomaly basically,
Yeah.
then on the boundary, we should have some edge modes, right? And
Yes.
like, what would these be in this quantum double setup? Like, that's
so
what I'm
it's
trying to understand.
yeah, okay. So normally, right, if we have an SPT on, for example, so okay, this is an SPT, this would be really an SPT for 1 plus 1D system, okay? So if you, okay, so we have to be a bit careful here with the terminology because an H2GU1 is really an SPT for a 1 plus 1D system. So if you think of it as a 1 plus 1D chain, then so I can, define this SPT. I can put it on a 1 plus 1 on a 1D chain with 2 boundaries, and then at the edges, I will have basically a projective representation of the group. Okay, I fully agree with this. However, in this case, we're taking what is really a 1 plus 1D SPT, but we're putting it on a purely spatial slice. So here, it's not a 2D SPT. Okay. Like, sorry, it's not an SPT for 2 spatial dimensions. It's so physically, this corresponds to an SPT in 1 plus 1D. But here we have a 2D, so a 2-dimensional space on which we are placing this, where we're not really thinking of this as a phase in time. So in this sense, it's a bit different to what you're asking about the edge modes, because I fully agree with an SPT, we have edge modes. However, as I said, an alpha 2, like an H2 class SPT gives edge modes at the edges of a 1D system. In this case, we're using the insights that we gained from the phases from it to basically implement a quantum logic gate. So this unitary is, as I said, from basically this co-cycle and then divided by the boundary counter terms in order for it to end. So it has a different physical meaning to the SPT to an SPT in 1 plus 1D, even though it's characterized by the same mathematics. As you see here, the boundary is one-dimensional. It's not, point. So that's why it has a different physical interpretation. Yeah, but thanks for the question.
I see. So one last thing. So there is this line of the boundary, and can we think of this as some defect inserted in this setup?
Exactly. Yes, absolutely.
Okay.
Actually,
So that
more
was
than
my question,
a
actually.
defect.
Maybe I didn't state it
Sorry.
correctly.
Yeah,
Because
actually,
when I was saying boundary, I was thinking of this one-dimensional line as some
Hmm?
defect that we couple, like along this line, we couple this new Hilbert space to the system. That's what
yeah,
I had
okay.
in mind.
Yeah, so let me, again, we have to be sometimes a bit precise. So sometimes terminology is used a bit inconsistently. So normally, so in a Euclidean setting, we use topological operator and topological defect interchangeably. However, usually if we're thinking of a time evolution, as we are in this case, where time is going up, then if we think of something that's acting on the Hilbert space, this is usually called an operator. And this is, so here, basically we think of our space as being this triangle, and then it's evolving in time. And so we are acting with an operator, this U, okay? Whereas usually the terminology defect is used for something that is, for example, placed at a point in space and then extends a long time. So this is just to save some terminology. But yes, we can, but indeed, in a Euclidean setting where we can do space-time transformations, then they're used interchangeably. And yes, you can basically think of this as an insertion of some, basically a topological defect in this setting, okay? Which we are now thinking of as an operator acting on our logical qubit and giving us these quantum phase gates. Yeah, but thanks for the question. I think it would actually be interesting to understand the actual, the physical consequences of this setup, because as I said, it's a bit different to what we usually think of as because usually, as I said, this 1 plus 1 DSPT is on a 1D chain, whereas here we're putting it on a purely 2D spatial surface with the bounded counter terms. Okay. Yeah.
Okay. Now it's more clear. Thank you for clarifying.
Yeah. Thank you very
thanks.
much. Thanks, everyone. Yeah.
Yeah, are there any other questions? Okay, let's thank our speaker again, and we can end the recording.
Great. Thank you very much.